Hey guys, today we're going to learn how to write noble gas notations. We're going to draw orbital notations to represent an atom's electrons in the ground state and understand how valence electrons are represented. Remember yesterday we had to write out those long electron configurations. Well, good thing is there is a shorter way to do it. So let's start with writing out the electron configuration like what we learned the other day. So krypton, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6. In rubidium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6, 5s1. Notice from here to here, these two are actually identical. So what we can do is we can draw krypton, the symbol for krypton, in brackets and write 5s1 because you're adding rubidium's extra step to what krypton already is, because it's the same thing. So the easiest way to identify this is you pick the last noble gas before the element in the question, and then add the energy levels and sublevels after the noble gas. However, helium and hydrogen do not have noble gas configurations, as their configurations are already condensed. So for example, sodium, we would write out as Ne, because that's just before it, 3s1. And for boron, which is right here, we would use helium. We'd write it out like He in brackets 2s2, 2p1. So you would use krypton whenever you're addressing this line, xenon whenever you're addressing this line, and so on. So let's do some examples. Cobalt is going to be argon, 4s2, 3d7. Silver is going to be krypton, 5s2, 4d9. Nitrogen is going to be helium, 2s2, 2p3. And cesium is going to be xenon, 6s1. So since you know how to write out the electron configuration, you should be able to identify the element by looking at the provided configuration. Remember, your last orbital is your biggest clue. So let's go ahead and practice. Use these and follow along your periodic table of elements and look at your last location. You should be able to identify immediately where your 3p4 is. And that's going to be sulfur. Then you look at 5s1, that's rubidium. 5p3 is going to be antimony. 5d6 is osmium. And 6s2 is going to be barium. Let's go ahead and practice on where we can find some errors in these. The first one we can notice, you can't jump from 2s2 to 3s2. You're missing a p orbital level in there. So we can identify that this one is missing. It skipped to p6. For number 2, right here, it goes straight from 3s2 to 3d5. It's missing 3p6 and 4s2. We can identify that it skipped 6 and 4s. And here, remember, if we're using noble gas notation, it needs to be a noble gas. And strontium is actually not a noble gas. You can look at your periodic table, group 18, and it is not located there. So this is incorrect noble gas notation. On this one, it follows 1s2, 2s2, 2p6, 3s2, 3p. You go from 4s2 to 4d10. That's incorrect. Remember, you jump from 4 down to 3, and then back up to 4 whenever you're going across the periodic table. So 4d10 is incorrect. It needs to be 3d10. 10. Then number 5, it looks correct. We can follow along 1s, 2s, 2p, 3s, 3p, 4s, 4d. That looks correct. However, your p levels need to be 6 to be full. Remember, the off-bow principle says that you need to fill up your lowest orbitals first before going to the next level. And here it's at 4, so it's not following the correct principle. So it actually needs to be 2p6 if it were to be correct. Therefore, 2p and 3p are not full. Orbital notation is another way to represent an atom's electron in the ground state. For orbital notation, we break down each sublevel into individual orbitals. So S has 1, P has 3, D has 5, and F has 7. This is a good visual for learning how electrons are placed along the energy level. Hund's rule states that in a single sublevel, each orbital gets 1 electron before any orbital gets a second electron. This just shows the spinning of the electron around the atom. So it's one spins this way, then this one also wants to spin this way. This diagram is correct. And then this one wants to spin this way too. Only if you have to add more do you have one spinning the opposite direction. They would rather spin one way before they spin the other. So it's like sharing a pizza with a lot of people. Everyone gets a slice before any person gets a second slice of pizza. Or like how every child wants their own bedroom before they're forced to share with a younger sibling. Pauli exclusion principle states that a maximum of 2 electrons may occupy a single atomic orbital, but they must have opposite spins. So they all want to go forward first. They all want their own bedrooms. They all want their own pizza. And then somebody comes back for pizza. Next person comes back for pizza, and so on, before you would fill up the next. So remember, electrons are negative, and like charges repel each other. So to force 2 electrons to share an orbital, they have to have opposite spins. So let's do 3p4, for example. Remember, p sublevels have 3 orbitals, so it gets 3 lines, and it has 4 electrons. So we all go one way, 2, 3, and then the 4th electron is going to come back for pizza. So here's what oxygen would look like. 2p4 means it has 4 electrons in its second energy level. And fluorine has 5, so you add the 5th one going down. Neon has 6. So you add the 6th one going down. Sodium has 3s1, so you start on the next energy level going up. And whenever you move to magnesium, instead of going to 3p, you stay on 3s. You want to make sure that that lowest state is filled before you move on to the next step. So you add this guy going back for pizza first. And then aluminum, you start up the next energy level, followed by silicon and phosphorus. Sulfur is coming back for pizza because he has 4. He's filling out his p levels. Chlorine has 5, and argon has 6. He is a full energy level. Potassium, you start back on 4s, 1, and then calcium has the second electron. Scandium, you just keep following it. And you fill out that 3d10 before you go anywhere else. And then the next one would be zinc, which is the 3d10. And you would just add that last electron before moving on to 4p1. So let's go ahead and draw out some orbital notations. Oxygen is going to be 1s2, 2s2, 2p4. So let's start out with your 1s. And he has 2 in 1s. So we're going to have 1, 2. 2s, he has 2 as well. So 1, 2, and then 2p has 3 spots, and he has 4 electrons. So you've got 1, 2, 3, 4. Magnesium is going to be 1s2, 2s2, 2p6, 3s2. It's easier if you write out your electron configuration before starting your orbital notation. That way you can follow along with how many electrons you have total. So 1s2, 1, 2, 2s has 2, 1, 2, 2p has 6. Remember, p has 3 orbitals. So we fill this out. 1, 2, 3, 4, 5, 6. And then 3s is 1 level, and his is filled out with 2 electrons. So next we have iron. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. So we start out with 1s, which is 1 orbital, and it's filled up. 2s, again, 1 orbital, and it's filled up. 2p is 3 orbitals, and it's filled. But we want to start with one way first, and then come back for pizza. 3s is filled. 3p is also filled. Let's come back for pizza. 4s is filled, and then on to 3d. Remember, you go from 4s to 3d, 5 orbitals, but he only has 6 electrons, so let's fill it out one way first. And then one of them gets to come back for pizza. Next we have bromine, which is 1s2, 2s2, 2p6, 3s2, 4s2, 3d10, and 4p5. I'm going to write its notation up here. We have 1s is filled, 2s filled, 2p is filled, 3s, 3p, 4s, also filled, 3d, and then 4p, but he only has 5 electrons. So we want to fill it out going one way, 3, 4, 5. Chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. So let's start off with the first energy level, second energy level, third, and then 3p, he has 5. So we're going to go up one way and back. 4. We have titanium. It's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. We follow along the energy levels and fill them up. 2p. Remember, p has 3 energy levels. We're going to go forward first and then come back. 3s, 3p, 2, 3, 4s, and then 3d. He only has 2 and 3. Remember, D has 5 energy levels, so let's fill out the 2 electrons, and that's it. Even though this is empty, we still want to leave it. So now that you know how to draw out the orbital notation, you should be able to identify the errors. Let's go ahead and see if we can find the errors in these. The first one, we have, it's correct. We have a filled out energy level. Second is correct, filled out. But here, notice we haven't all gone away, and somebody's coming back to steal pizza. So the problem is that this one should actually be over here. Alright, and then the second one is correct. It starts off right. Got a filled out first orbital, filled out second orbital, but here they've added a second energy level. Remember, S only has one energy level, so this shouldn't be here. And here's the written out answers if my writing was so bad. So for the third problem, we have a filled out first orbital. Correct. 2p has 3 orbitals and they're all filled out. 3s is filled out. 3p is filled out. 4s is filled out. But the problem is it goes from 4s to 4p. And that's skipping all the transition metals in the middle. So we need to insert a 3d right here. That's the problem. A 3d with 5 energy levels. Alright, next problem. 1s looks good. 2s looks good. 2p looks good. 3s looks good. 3p is fine. 4s. This one does go down to 3d, so it's correct. But you see how we have an empty energy level, but these ones are filled? It should be where they all go out for pizza first and then come back. So they just left out this one from being filled up. Also, since it wasn't filled up here, we shouldn't have moved on to 4p because you want to fill out your ground state first before moving up to the next level.